Okay, I'm going to talk about atomic mass. So, atomic mass is the mass of one atom of an element. Now, that's not a mass that we often deal with in, general um, chemistry type of experiments because most of the time we're working with macroscopic samples, so samples that we can actually see, which definitely consist of more than one atom. Okay, and so if we talk about the mass on the scale of an atom, it isn't as useful to us if we're working with a lot of atoms. Um, and so it kind of depends on, what you're doing. But that term atomic mass is saying this is the mass of one atom. Okay. Now we quantify that typically in units of atomic mass units, or AMU. And just to give you an idea of the scale of that, an AMU is about 1.6606 times 10 to the negative 24th grams. So it's really tiny. Okay, because a gram is on the scale of things that we deal with, so like about a paper clip or so. Um, and so that is on the, the scale of, or grams is on the scale of things that we deal with, or even kilograms, some people will say is a better scale for, realistic objects. Um, but if you want to talk about individual atoms, if you quantified their masses in grams, then you have to write these really tiny numbers, or you write in scientific notation all the time, right? So we wouldn't typically use AMU for our regular samples. But if you are just focused on one atom at a time, you would use AMU, or even just a few atoms, you would use AMUs. Now, instead of talking about one atom at a time, you usually have a sample that contains lots of atoms. Now, if that is of the same element, then we want to quantify the mass of a sample of an element. What we would utilize is what we call the average atomic mass. Okay, so the average atomic mass is the weighted average of masses of each isotope of a given element. So what you have to know is that when we have an element, this element's made up of individual atoms, right? And typically we would think of it as if we have atoms of an element, they're all the same, okay? They have the same properties and everything, but they're not exactly 100% the same, okay? There can be some atoms that are a little bit different. And so you can have atoms that have a different number of neutrons, but they're still the same element, okay? And if there's a different number of neutrons, they actually have a different mass, okay? And a significantly different mass, okay, on the scale of atoms. Um, Now, if you have an atom and you take an electron away or you add an electron, it doesn't make a big difference on the mass because electrons have very small mass relative to the rest of the atom. Okay, but neutrons are significant in mass of an atom. So having more or less neutrons makes a big difference. So when we work with samples of elements, typically we just work with a natural sample. Okay, and that sample is going to be composed of a mixture of all the, regularly occurring isotopes of that element. And so the mass is going to be a combination of their masses. And it can't simply be quantified as a typical average. So summing things together and dividing by how many. So if we have two different isotopes, we can't just take the mass of one isotope plus the mass of the other and divide by 2. That would only be true if it's in a 50-50 ratio. Okay. But if the naturally occurring, abundance of things is not 50-50, then that mass is going to be weighted more towards whatever is more abundant. And so what we utilize are these average atomic masses. And so it tells you on average what each individual atom of an element weighs. Okay. And how that is calculated is by doing a weighted average. A weighted average you calculate by taking the portion of something, so typically the percentage times that quantity. Okay, and so in this case, since we're talking about atomic masses, you take the atomic mass of an isotope times that isotope's percent abundance. Okay, and you would do that for each isotope of that element, and then you would sum those together. Okay, and that would give you the average atomic mass. Now, luckily, we don't have to do this a lot because it's all really been done for us, or at least for elements that are really well known, which is most of what's on the periodic table. And so these are the values that you actually find on the periodic table right along with the atomic numbers. Okay, so when you look at the periodic table, you'll have these whole numbers that are increasing across the rows. And as you go down the periodic table, those are the atomic number. Those are the number of protons in an atom of each element, which is constant, even if you have different isotopes of an element. But the mass is different for different isotopes. And so that's where these average atomic masses come from. And that's the other value that's typically on a periodic table. It's the one with the decimal places. And so that is the weighted average. And so that's already kind of done for you. So most of the time, if we want the average atomic mass, we just go to the periodic table. Usually we don't calculate it, but you can. Okay, so we'll look at an example, of how those are actually quantified. But most of the time, when you need it, you just go to the periodic table. So here's an example of how we would calculate an average atomic mass. So I give you some data here about chlorine. Okay, and I want you to calculate the average atomic mass of chlorine from the isotope information given. So chlorine exists as two isotopes naturally, as chlorine 35 and chlorine 37. Now, you can rewrite these. You could write chlorine 35 as 35Cl and chlorine 37 is 37Cl. And you could even put the atomic number there, 17 at the bottom of each of those. And that's saying the same thing. It's the same isotope we're talking about. Okay. But what's given here is the atomic masses. So we have the atomic mass of each isotope. And so for chlorine 35, it's 34.9689. And for chlorine 37, it's 36.9659 AMUs for each of them. Sorry, I should not drop that unit. Don't ever drop units. They're very important. And then we have the percent abundance of each of these. Okay, so that's the percent abundance of chlorine 35 is 75.76, and chlorine 37 has a percent abundance of 24.24%. Okay, and so what we would do is we would take the percentage of each of those times their mass, and then we would sum the results together, okay, to get the average atomic mass. So the average atomic mass, I'm going to kind of abbreviate that, is going to be equal to the mass of one isotope, so 34.9689 AMU for the chlorine 35, times its percent abundance. Now, when we plug percents into math equations, you convert it into the decimal form. So you shift the decimal place twice. So we would multiply it by 0.7576 because that is what 75.76% means. And then we would add that to the product of the other mass, 36.9659 AMU, times its percent abundance of 0.2424. Okay, and that would give us our average atomic mass. So if I go through and do that, and I'll even do it stepwise, I have the 34.9689 times 0.7576. And so let me just get the result of that first. and that is 26.492. I'm going to write it down to 5 sig figs because that multiplication should be 4 sig figs, so I'm going to keep an extra one. I'll do the same for this next one. 36.9659 times 0.2424. And I'll write that one down to 5 sig figs because since I'm not done with the calculation, I will keep an extra sig fig. Okay, and so remember multiplication division, you keep the fewest sig figs. So we take a 6 sig fig number and multiply by a 4 sig fig, we round to 4 sig figs if that was the end result. If not, keep an extra till you're done. And so then I'm going to add those values. Okay, so I'm going to add these together. So I'm going to take 26.492 and add it to 8.9605, and that gives me 35.4525 AMU. And that one, I still need to round to the appropriate sig figs. So since it was an addition, I look at the uncertainty in these values. So this first one has uncertainty, sorry, because this has extra sig figs. It's not in the 2. That 2 is my extra digit. The 9 is where my uncertainty is. So the second decimal place. And this other one has the uncertainty in the third. And so I should round to the second decimal place, so that 2 isn't going to affect it. So my answer would be 35.45 AMU as my average atomic mass. And if you look at the periodic table, you find chlorine. That should be what you see as the average atomic mass. Now, depending on what periodic table you look at, they may give you more decimals than that. Generally, when you pull those masses off the periodic table, you shouldn't ever have less than 2 decimals, unless it's one that's all that's given on the periodic table, okay, which is pretty rare. There are a few elements, even the radioactive ones, some of those, they don't give you any decimals because they don't have them more accurately. But in general, if they give you at least 2 decimals, that's what you want. But this calculation you can compare to the periodic table and it should match. Okay. Okay. So that's kind of the basics of where does that average atomic mass come from. But like I said before, lucky for you, you could generally just look at the periodic table and happily take that and be happy that someone else did the work for you. Okay, because we don't need to keep recalculating that, because every chlorine sample that we use, this is applicable to if we're talking about a regular mixture of isotopes. Now, I do have one more example here with some questions, and some of these are a little more challenging to see if you really grasp it. So here I say boron has 2 naturally occurring isotopes. Okay, now realize chlorine has 2 and boron has 2. Not every element has 2 isotopes. We've seen earlier hydrogen's got 3. Okay, some only have 1 naturally occurring. Some have 5 or 6 or more. So that's not something that's easily predictable. That's something that is determined based on lots and lots of studies. Okay. But here I tell you, there's the 2 isotopes, boron 10 and boron 11. And I also give you their atomic masses in parentheses. And I want to know, according to the periodic table, what's the average atomic mass? So this, of course, would require you to have a periodic table in front of you. I don't have one on the screen, but I have one right behind me, so I can look. And it's 10.811, so I'll write that down. So the average atomic mass is 10.811 AMU for boron. Okay, and like I said before, depending on what periodic table you look at, you might be given more decimals. You want to keep at least 2 of them, okay, so that you're not integrating excess error in your calculations. Now, the next question, I say based only on comparison of the average mass with the isotope masses, identify which isotope of boron is most abundant. Okay, so this is more of a conceptual question. Okay, so you look at these masses, the average is about 10.8. And then if you look at the mass of boron 10, well, it's about 10, right? Just like the mass number. It's not exactly 10, but it's about 10. And then boron 11 is about 11, just like the mass number shows you, right? It's pretty close. It's still a little bit off from that. But when we think about this, if any sample of boron contains a mixture of those, and if on average it's around 10.8 AMU, you just look at that mass and think about which one is it closer to. Well, 10.8 is closer to 11 than it is 10. So that must mean that in a naturally occurring sample, you have more boron 11 atoms than boron 10. That's why the average mass is weighted more towards that 11, okay? And so 10.811 AMU, AMU is closer to 11, 10, so boron 11 is more abundant. Okay. And so that's just seeing if you kind of understand what the weighted average does. So a weighted average is always going to favor the things that are more abundant, right? It's going to be closer to that. Okay, now the last one I have here is calculate the percent abundance of each isotope of boron. Now this is kind of a tricky one. This is kind of a challenge one. But let's think about the information we have. We have the atomic masses of each isotope, and we have the average atomic mass. And we're looking for the percent abundances. So we have a relationship between all of that stuff, right? And so the average atomic mass, 10.811 AMU, should be equal to the mass of each individual isotope times their percent. So 10.012937 AMU times the percent of boron 10, okay, and then plus the mass 11.009305 AMU times the percent of boron 11. Okay, so we have an equation that has the two things that we're looking for. Okay, but unfortunately, we can't solve one equation for two different things. Okay, we need more information, right? And that's the challenging part here. So that's where you need to be able to piece together a little bit more. So the key here is we say that boron has two naturally occurring isotopes, okay? So only two. So you're not missing any other information. There's not more pieces to that equation, okay? So what you need to realize is if it only has two things, then those make up the entire possibility, the entire sample. If you have a sample of boron, it's only boron 10 and boron 11. Okay, so really the percent of boron 10 plus the percent of boron 11 should sum to 100%, or if you want to put that in the mathematical way, it would sum to 1, right? Because you're plugging in decimal forms of these things. So 100% is the same as the number 1. Okay, so now we have a second equation that relates those two unknowns. So we actually have two equations, two unknowns. Everyone should have done some algebra before, and so that's a situation commonly encountered in algebra. You solve one equation for one of those things, plug it into the other equation, and solve for what's left, okay? And so I'm not going to go through all of that algebra. That's something that you can sit down and do if you want to check and see, just test your algebra skills, because you need pretty good algebra skills in chemistry. I'll tell you what it's going to come out to is the boron 10 let me write this in a different color. I guess the boron 10 is going to come out to about 20%, and the boron 11 is going to come out to about 80%. Okay, if you went through and checked that. And so that, like I said, that question is a little bit more challenging than you might really need to know, but it's a good check. Do you really understand what average atomic mass is?